Thanks, Ann. The list of speakers for this year is an always evolving thing, and there's still some gaps to be filled. But so if anybody's interested in giving a talk, please contact me. I'd love to hear from you. But for tonight, I'm really excited to present to you two of our research geologists, the Arizona Geological Survey, Gootee and Tawnya Wilson. They are part of our small but really exciting group we're just starting to get into the subsurface resources in a big way. Turns out there's more and more interest, and that means funding to do this kind of work. And so I think we really have a lot of potential in Arizona for a variety of different things, which they'll be talking about. Brian started with us in 2007, and he's done a lot of different things for us. He's really a jack of all trades. So we asked him to do too much, actually. And he never says no. I mean, it's weird. But so anyway, he's done a lot of different things and a lot of work in our mapping program and other things. But the past maybe 3 years or so, 3 or 4 years, we started to really get into the basin subsurface stuff, and he's the leader of that group. Tawnya Wilson we hired 3 years ago. Okay, time flies. To join that group, and she has a background in the oil industry, in waste disposal related to the oil industry from West Texas and that stuff. So she had a great background and really tied in well and complemented the other members of our team. And Lisa Thompson in Flagstaff is the other member of the team. And so anyway, they're a great group, very dynamic. We have a lot of cool projects going on in that group. And so I'm sure they'll be able to give future talks as well. Some of those come in, but want to come on up here? I don't know, yeah, it's a good test. There you go, Brian.
Okay, great. Thank you. Can you hear me? It's good, great. Thank you, Phil. Thank you, Mike Conway, for setting this up and organizing everything, and to everyone else, including the back, who helped us set up the slide deck and polling app. So happy to be here. Last time I was here, I gave a talk on Big Sandy Basin, which was super fun ahead of a cool field trip that we led last April. And so now we're talking about basins, but just a lot more of them. I'd also like to thank Tawnya Wilson for agreeing to giving the talk tonight. She could have said no, but she's following in my footsteps quite nicely. And I'd like to thank Lisa Thompson. She's also part of our team. She couldn't be here tonight, but the three of us would have split it up 3 ways because we have 3 cool topics to share with you tonight: gas storage, sequestration, and geothermal. And so these 3 topics are related to the deep subsurface and about energy-related topics and energy resiliency. And we focus on energy resiliency because that's the direction that a lot of our stakeholders in Arizona are aiming for, and we're here to support that effort. So with that, I'll just kind of get into it. I think this... Okay, so we'll jump into this map. This map shows a distribution of sites across the U.S. that have some established subsurface pore space or storage energy-related project. In yellow are the gas storage sites, where underground gas storage is typically stored in gas caverns, solution mined salt caverns for gas storage, mostly, almost predominantly. And then carbon sequestration sites, whether they're enhanced oil recovery sites as older places like the Permian Basin, or new sites as of 2023. And then geothermal sites in the West Coast. All of the geothermal amounts to about 4 gigawatts of power, more than any other country, but it's still pale in comparison to the other energy reserves. The carbon management, I mean, this site is already different. I think just in 2024 alone, you can add a few dozen black circles to this map. And we actually had a hard time trying to find out where to put them, but this is the current distribution of these kinds of efforts in the subsurface realm. And so our focus of this talk is going to highlight really just these 3 areas and how they relate to each other, what's the interplay what's the regulation and liability that comes along with these kinds of projects, and how do they fit into the energy transition when we're talking about energy production and energy-related wastes. And we'll start with this conceptualized stratigraphic section on the left. So our outline will kind of follow the direction we're going to go. We have a generalized section shows the tallest tower in Tucson for scale at the very top, at 330 feet. And the rest of the section below is to scale. So in some of the basins, and several of them, you'd expect to find these kinds of strata. You have freshwater reserves down to 2,200, 2,500 feet. And then you get into saline, hypersaline, mixed deposits, bedded salt deposits, where gas storage seems like a very viable option for our salt. And below that, saline reservoirs and porous media, sandstones, conglomerates, that kind of thing for carbon sequestration and storage. And then below that, another stacked storage kind of concept where you can mineralize CO2 with alkaline rocks such as mafic and ultramafic rocks, which we do have quite a bit of. And then below that, the potential for enhanced geothermal systems, which we're going to focus in on that one, not the other types of geothermal. And that'll get us through the first 4 bullets, and then we'll kind of highlight how do these all fit together in a distributed energy ecosystems model. When you're talking about one basin, one site, one region, how do they relate to each other? What should we expect in terms of risk and liability and rules and statutes that the state needs to prepare for in advance of these projects coming? And then some of the projects we're working on now. And so I will turn it over to Tawnya, and she'll focus on sedimentary basins.
Thank you. That big guy. Awesome, thanks. Hi, everybody. All right, let's advance the slide here. So I'm going to start us out by talking about sedimentary basins throughout Arizona. That is the primary research focus of our basin analysis team, and a lot of the activities that we'll be talking about this evening take place in these basins or proximal to them. So the map on the left-hand side is of Cenozoic basins throughout Arizona, shown in the yellow polygons here. Actually 57 basins within Arizona's Basin and Range province. Many of these basins are deep asymmetrical extensional basins that are bordered by crystalline bedrock and have been filled with porous and permeable volcaniclastic and siliciclastic sediments. Some of these large basins are co-located with some major metropolitan areas, such as in Phoenix and Tucson, and they are also nearby pipeline infrastructure, which are the blue and red lines on the map, as well as interstate highways. So these are important things to think about for future development. And then on the right-hand side is a map of the Paleozoic basins in Arizona. Most of these are up on the Colorado Plateau in the north. These basins are characterized by sedimentary strata that are gently deformed due to a north-northwest folds. And they also contain confining strata such as shales and salts, as well as porous and permeable rocks or reservoirs, such as the Coconino sandstone or units from the Supai group. So all of this to say that there are lots of different basins throughout Arizona, both in the Basin and Range and on the plateau, that have good potential for storage. So with that, I'll get into this extensional sedimentary basin model. And we're really showing this because we're going to come back to it a few times throughout the presentation. So this really highlights the type of basins we would see in the Basin and Range, and we're doing that because they are most predominant. So up in the left-hand corner is a block diagram. This just shows the depositional model, essentially. So during a Basin and Range extension, you created these highlands and low-lying areas due to subsidence from tectonics as well as sediment loading. You filled in these areas of accommodation with sediments from the surrounding highlands and also waters before there was any outlets or river integration here. So if we jump down to this schematic, this represents, again, a deep asymmetric basin. And this gray area down here towards the bottom is representative of mafic rocks or basalts. During extension, we had volcanism that produced lava flows on the surface that have now been downfaulted into some of these basins. The basin fill here, again, volcanic and siliciclastic rocks ranging from salt to cobble size from the surrounding highlands. And then in the basin center here, we have our bedded salt deposits or evaporite deposits. These, again, would have formed as the waters trapped within the basin evaporated over time. So just keep this model in mind as we move forward and talk about these different elements. Ooh, and I realized, oh no, how do I go back? Let's try this. Okay. Sorry about that. I forgot to mention here, I did put the formation waters on here as well, which is important to note. You see the water table closer to the surface, and the formation water generally increases in salinity with depth, especially when you have large salt deposits. All right, so now we're going to move into our discussion about gas storage in salt caverns. This particular photo is of salt flats and Badwater Basin in Death Valley National Park, and it's just a good modern analog for what some of these basins would have looked like. Okay, so we're doing something a little bit different tonight. At the start of each of these sections, we're going to have a poll or a question for you all to kind of get you guys thinking about these things. So if you can scan that QR code with your phone, when you open up your camera and point it at the screen, it should come up with a link. Click that link and it'll take you to a website that has this question on there. So the question is how many salt caverns are used for storage in Arizona? And you can go ahead and put your answer in and hit submit. And once you do that, the results will show up on the screen momentarily. So I'll give you all one more minute to kind of do that. We're gonna do this, I think there's 2 more questions, so. Okay, I think we're gonna go ahead and advance. All right, so it looks like 41% said 3 to 5. And the way that the question is worded, that is the right answer. There are, I'll get into it a little bit later, but there are 2 primary locations or sites for gas storage in Arizona, but there are multiple caverns there, so I'll explain that in a minute. All right, but first I'm gonna talk a little bit about underground energy storage resources in salt in general. So salt is quite unique. It has low density, it has low permeability, which means you can store really small molecules of gas. It has high solubility in water. It doesn't undergo brittle deformation. It moves more like a plastic, so it can self-heal fractures, and it has minimal reactivity chemically, which makes it a good storage container. But salt caverns are not natural, they have to be engineered. And so this diagram on the bottom left kind of shows that. This is an example of like a bedded, bedded salt deposit where you have these light gray layers representing the more pure salt and these thin brown inner layers where it's less pure, for example. So here you would drill a well and you'd inject fresh water into the well, and that would eventually start dissolving away that salt rock and form a cavern. And that cavern would be then filled with the brine created from the dissolution process. And then you can inject your storage gas or fluid and deplace that brine. And that brine can either go in a brine pond at the surface, or it can be re-injected through like a saltwater disposal well into a deeper reservoir. Now on the right-hand side of the screen, I've included this image here. This just shows the different types of gases or fluids that could be stored in these salt caverns. So here is listed as hydrogen, compressed air, crude oil, and natural gas. A few that aren't listed are helium, methane, ammonia, CO2, for example. The crude oil and natural gas have been stored underground in salt caverns for decades. The US has the Strategic Petroleum Reserve in multiple caverns throughout the US. It's kind of like a rainy day fund if we ever have a large demand for those resources. Hydrogen is a little bit newer. It has been stored since the 1980s, but there's a lot more research going on surrounding hydrogen. So some advantages of using salt caverns for storage are that they have high capacity. You can store large volumes at depth. They're generally safe due to the unique properties of salt and low risk for leaks. And they are more cost effective to have salt caverns created in the subsurface rather than having that storage built out on the surface of the land. And then they are flexible, so you can withdraw fluids and gases as needed. So we'll highlight some salt cavern gas storage sites in Arizona. So there are 2 storage sites, the first being the Holbrook Basin. Let's see, oops. Oh boy, there we go. The Holbrook Basin up here, located at the red star. This is also called the Adamana Storage Site. There are 2 caverns here, and they both store liquid petroleum gas. The second being the Luke Basin, also known as the Bumstead Site, and that's located in the Phoenix Metroplex. There's 3 caverns here, and they're also used for LPG storage. The caverns at Luke, we have a little bit more information about them, so the rest of the images and graphics on this slide are about that site in Luke. So those caverns are about 1,000 feet tall generally, and the top of those caverns start around 1,600 to 1,800 feet below the land surface. At this location, there is also solution mining for salt. So Morton Salt Company, I think, owned and operated that operation. So the pictures up here, the first one is of one of the wells at the Luke or Bumstead site. So you can see the wellhead there, and this is connected to one of those wells that penetrates all the way down into the cavern. And then to the right of that is a image of the brine pond. Down below on the left-hand side, this is a 2D seismic line that was shot by Exxon in the 1970s. This particular figure is from an Eberly and Stanley paper where they've interpreted the location of the salt body, so I've just highlighted it here. It's about 10,000 feet thick. So this is really a world-class site here just because of, not only because of the thickness, but also because of the purity of the salt. Now, on this figure too, there's this little yellow, there we go, this little yellow polygon, and this is representative of the actual salt cavern. So these 2 images on the far right are they're produced from sonar, so they sent a sonar tool down the wellbore and were able to get 3D images of what the cavern actually looks like. So the first one shows you in a vertical sense, and then the second one there is if you were looking down the wellbore into the cavern. And the warmer colors represent a larger diameter. And these types of images are taken as part of a mechanical integrity test that for this site is done every 5 years to ensure that they have good integrity of the cavern and there have been no major changes to the shape and size over time. All right. At AZGS, we are getting into embedded salt research, which is mostly prompted by stakeholders in industry asking about hydrogen storage in these salt bodies, as well as compressed air. So we've received some internal funding from U of A to better understand the salt deposits throughout Arizona. Part of this project was creating an Arizona salt core inventory, so trying to track down where we actually have samples. There's an example on the far left here of one of those boxes of salt core. But we have had to travel for some cores, but we also have our core repository up and running at AZGS now. So on the right-hand side is a map. There's a QR code there. This is a publicly available map that we put together that really just shows where the salt deposits are, or what basins have salt in them. You see the 2 blue dots, those represent those 2 sites I previously mentioned in Luke in the Holbrook Basin. And then the colored polygons, the red is where we have developed caverns, the blue is where we know there is salt, yellow are play, so they're in exploration mode, and the green are unknown but likely and warrant more exploration. And the blue dots on there represent how many salt samples we actually have. So we're collaborating on this project with Los Alamos National Lab, where we've sent them a suite of salt samples for them to do testing, so to better understand the physical, chemical, and mechanical properties of those salts. So those results are pending. And then this picture here, this is our basin team, so Brian, Lisa, and myself. We are 2,100 feet underground under Carlsbad, New Mexico. This is at the WIP site. It stands for the Waste Isolation Pilot Plant. This is run by the US government, where they store low-level nuclear waste. But Los Alamos National Lab also does research down here related to hydrogen storage in salt caverns. So we got to go see that firsthand. All right, so this is the extensional sedimentary basin model that we're looking at again. And I've just put on here the elements associated with gas storage embedded salt. So we have the gas injection well, the storage caverns in the salt, and then I've also added a potential saltwater disposal well here. And as you go through this, we're going to add to this diagram. Okay, we're moving on to carbon capture and utilization and storage, so CCUS. This particular image is a drone photo taken by Brian of the Harquahala Valley, and this is one of our sites of research, which I will talk through in a moment. But first, we have another poll. So if you want to scan the QR code again, this question is, what is the nominal minimum depth required for CO2 storage in a saline reservoir? And it looks like we have a live poll going. Maybe. Yep. Okay. So, if you answered 2,600 feet, looks like 71% of you did, you're correct. And I'll touch on that a little bit more here in a minute. But first, I'm going to talk through carbon capture, or CCUS, kind of a process model. So we'll start over here on the left with sources. So sources of CO2 could be transportation, electricity generation, industrial processes. And to capture that CO2, there's 2 different methods that I'll talk about, although there are many carbon dioxide removal methods. The 2 I'm going to highlight here are post-combustion capture, which really, if you, for example, have a power generating station, you are directly capturing from that source. Direct air capture is another method, and this is essentially taking air, or taking carbon from the air or the atmosphere. So that would include legacy excess carbon in our atmosphere, as well as whatever's being currently producing today. So once that CO2 is captured, It's generally compressed and liquefied. With heat and pressure, you get it to a supercritical state, which makes it much easier for transportation, which is typically done through pipeline and has been done for many years that way. But it also can be trucked. And then there's two different outcomes here. It can be used. Companies can use it to make fertilizer, to make delicious sparkling beverages, metal fabrication, concrete, even enhanced oil recovery. The other method is storing it. So there are incentives to store carbon permanently underground for businesses, such as the 45Q tax credit and carbon credits on the market. So the storage type that we're going to get into today is geologic storage. So this block diagram on the left here just shows the different layers that would be involved in the subsurface. So the fresh water up at the top, let's see if this works. Fresh water down to this cap rock, below that the permeable sandstone and saline water, and then basalt at the bottom of the diagram here. At the land surface, you see we have the direct air capture, and then there's also a power plant that is using that post-combustion capture method. So what we do here is use non-potable, so hypersaline water, and mix that with CO2 at the surface, and then that is re-injected. So the different storage types we have here are deep saline aquifers, depleted oil and gas reservoirs, which we don't have much of in Arizona, and mineralization and mafic rocks. There is the potential to also store in fractured basement rocks. But saline aquifer storage is probably the most viable storage type in Arizona. And so there are some requirements associated with this. So we need a rock that has high porosity and permeability. We need space to actually store the CO2. We need a competent and robust sealing unit. The depth, which goes back to that question, generally is greater than 800 meters or about 2,600 feet, and this keeps the CO2 in its supercritical state. TDS needs to be above 10,000 parts per million, and minimal geologic risk, such as low seismicity. So I mentioned CO2 mineralization, so I'm going to talk about it a little bit here. So the general process is that you would take basalt or a high magnesium mafic rock and combine that with CO2 dissolved in saline water or sodium bicarbonate mixture and form solid carbonates such as magnesite, siderite, calcite, and others, along with some residual clays and silica. The chemical reaction can be induced either underground or at the surface. So this example on the bottom left is from CarbFix, their company that mainly operates in Iceland. Their figure here shows the, the direct air capture setup here, where they've captured CO2, they've concentrated it, mixed it with water, and put it down a well into the subsurface, into a basalt. And that CO2 turns into stone, usually less than 2 years. And then that CO2 that is now a rock stays there permanently, but there is hot water that they can remove from that reservoir and bring to their geothermal power plant. And so that power plant helps power the whole process for CO2 capture and storage. So in Arizona, AZGS is currently investigating CO2 mineralization, but at the surface level. So Lisa Thompson on our team leads the project really to build an inventory of rocks throughout Arizona that we can use, that can be used for CO2 mineralization. We are working with colleagues at ASU and NAU for this. So this picture here is from the San Francisco volcanic field, just showing the different types of mafic rocks at the surface. And I believe 17% of Arizona's surface is covered in mafic material. This process also works for alkaline waste material such as mine tailings, and that's something that this group's also looking into at this time. So the viability of CO2 mineralization in Arizona in the subsurface is something that we haven't explored much yet, but we are really hopeful that it can work here, and it's something that we will be looking at in our project, our CO2 HQ Carbon Safe 2 project. So this project, we were recently awarded from the U.S. Department of Energy a Carbon Safe 2. And now this project will be looking at the Harquahala Basin specifically, which is about 60 miles west of Phoenix. And I know there's a lot on this slide. We're not going to get to all of it in detail, but we'll start here on the top that looks at the, this is kind of the timeline for these Carbon Safe 2 projects. So it starts with phase 1, which is pre-feasibility, and that we've accomplished that pre-feasibility study, I guess last year. And we applied for the phase 2 and were awarded. So we are currently in negotiations with DOE now and anticipate to start in March. So as part of this project, we're going to be collecting new data. So we're going to be drilling a strat test well, and we will be doing 2D seismic survey. So I'll direct you to the map in the center of the slide here. That strat test well is where this pink dot is, right in the middle here, and those yellow dashed lines are the locations of our 2D seismic survey. The red polygon is the potential CO2 reservoir. The kind of greenish polygon is the extent of our salt unit, and then the purple is a modeled CO2 plume. So with this new data collection, this map will certainly change and improve. We're going to be doing lots of data integration and modeling. We'll be looking at risk and creating a risk mitigation plan, or MRV plan, and also looking at community benefits. So this is a $12.3 million project that we are awarded, but we are also working with 8 different cost share partners. They're major utilities within the state, as well as different industry partners. So although this is a Carbon Safe 2 project, and we're looking to see if this basin can store CO2, there are also other elements at play here that our partners are excited about. So there is the potential for salt cavern gas storage, CO2 storage, CO2 mineralization, and potentially geothermal here. Okay, this is the extensional sedimentary basin model where we have CO2 injection wells and our CO2 source here. So we'll stay tuned for see how that develops. So I'm going to hand the mic back over to Brian to finish out the rest of the talk here.
All right. Thank you, Tawnya. That was awesome. Okay, great. So this third category of subsurface energy-related projects is enhanced geothermal potential, and would like to start off with my personal sort of poster child, the Ford site operated by Fervo Energy in southern Utah. And so they're actually taking advantage of DOE's funding initiatives to advance a site for quite honestly, a place that would look much like Arizona. We would call these blind geothermal sites, which, you know, you can't see a manifestation at the surface, but there is potential in the subsurface, and they were able to identify that and tap into it. So this is going to be a reality at this site. I thought this would be appropriate segue into this category. But first, what is the hottest bottom hole temperature recorded in Arizona? And this is another one of those live polling ones, so don't look at the screen until you've submitted your answer. Okay. Yeah, I think we had 16 on the last entry. There we go, 17. All right. Believe it or not, the answer is 750 degrees Fahrenheit, 400 C, which is pretty incredible. Not everywhere, of course, but at least in 2 or 3 places, those are the bottom hole temperatures, which is really exciting. Okay, what is EGS and why is it different? It's different from other types of geothermal power. We've got heat pumps at the shallow subsurface. There's this stuff called advanced geothermal systems. Let's see what else. Conventional geothermal. Those don't apply here. Enhanced geothermal systems are basically engineered geothermal systems that take advantage of deeper high-grade heat in the 3 to 5 kilometer range. So in this scenario, the diagram on the left shows you have a power facility, you have 1 injection well and 2 producing wells in this cartoon diagram. And you have some sort of condition at these depths that maybe they're not ideal. Maybe the heat conductivity and the transfer is not there. Maybe the fracture system is not there. The permeability is not there. So in these cases, you can engineer your way through that. You can introduce fluids. You can drop in cold water. You can drop in CO2, some other liquid media into this environment. You can frack it, and then you can withdraw the heated water, providing there's enough heat transfer in that environment. And so this is the basic principle behind enhanced geothermal systems. The systems can be a little bit more simplified, like a conventional closed loop system where you have 1 well inside of another and you're keeping it all self-contained. They're less efficient than this open sourced system where you have 2 or 3 or 4 wells that have varying elevations and lateral feet. These don't have feet in the diagram, but they can easily have lateral horizontal well drilling that connects the system together. There are several advantages to EGS. I mean, it's renewable energy, so the concept is that it would be renewable for indefinitely, providing you can meet certain requirements on the materials that you have in that environment. The costs are high, but if the infrastructure is put in place, then it can last a long time. Oh gosh, there's so many advantages I kind of forgot as soon as I came up here. But they have a really small footprint. You can have EGS operating on a site that's only less than a few tens of acres. You can have distribution at depth within that small footprint, so you have you can have multiple sort of diffuse areas of EGS opportunities within one site versus just one storage site like in a gas storage facility. You can also leverage the oil and gas sector and the workforce and the technology. They have all of the abilities and the know-how to advance these kinds of sites. So there's a real potential for that sector to grow into geothermal. You just need the funding. So once the funding is there, the development will follow. And so we see some potential for EGS as possibly the next boom following solar and wind, the last 2 previous booms. So in that light, the enhanced geothermal shot is something that the Department of Energy has put forward as part of a series of earth shots. There's a hydrogen earth shot, a carbon shot, and there's a geothermal shot. And their initiative and goal here is to provide, I think it's $45 per megawatt by the year 2030 to lower the cost. And by the year 2050 to provide at least 90 gigawatts of power from geothermal, which is really ambitious, but it's totally doable. So the there's going to have to be some hurdles to overcome, but that's currently where the initiative stands. One of the challenges of these sites is that they are expensive. The investment initially is high, and you do have some permitting barriers that are always a complaint of any EGS site. One of the unknowns about geothermal at depth is we don't really know a lot about the potential for the heat transfer coefficient. That implies that you actually know what kind of heat transfer is going to occur from what particular rock type. So some are really conductive and some are not. And so that's kind of one of the gambles you have to take. But with EGS, you might be able to engineer your way around that. Okay. The technology is changing. It's pretty amazing. I think some of the geothermal technology offices offered these technical forums lately, and we've been learning a lot through that and through some of the partners that we've talked to. The drilling technology has advanced so much that it's really putting geothermal into a completely new light. So if you go back 4 or 5 years ago, to drill a 12,000-foot well, it would take you about 150 days, drilling at about 15 feet an hour. And last year, the Fervo site, they were able to accomplish 75 to 100 feet an hour and drill a 12,000-foot hole in about 15 days or 2 weeks, which is a complete game changer in the way you approach the development of these sites. Combined use of an EGS site is pretty spectacular. You can use these kinds of facilities to power all kinds of things. You can co-power them with solar to make it a much more efficient system. You can power direct air capture systems through geothermal, like Climeworks and Carbfix out of Iceland. And you could, basically it's a lot of waste heat that data centers are really attracted to. And there's even been some places where Bitcoin has invested in geothermal wells just to power the Bitcoin processing system. So there's a long array of a list of areas to use. You can use electrolysis powered from geothermal to just break apart methane or other gases to create green hydrogen, for example. So geothermal can fill that gap, and that makes it a pretty exciting area to grow into. As far as Arizona goes, the map on the left is kind of a ballpark figure of what we see Arizona in terms of its geothermal data set and its potential. So I realize it might be kind of hard to see some of the values on here, but largely speaking, we have less than about 100 data points that make up our thermal sort of spectra for the state, and in comparison, that's not very much data. When you look at states like Texas, they have several 100,000 thermal data points. So it's completely different. We're not an oil and gas rich state, but the base map is created from sort of a complex model of crustal thickness, these kind of heat fluxes, bottom hole temperatures, to put together an array of what Arizona would look like at a 5-kilometer depth slice in terms of geothermal potential. And so it's ranked with the warmer colors being towards a higher heat flow or heat flux. And this is generally the case for Nevada, Utah, and other western states. They have these really warm areas that are favorable for geothermal. So that's definitely a bonus for Arizona in terms of heat flow. We have several warm, hot, and super hot springs. And again, we have a few data points that are in the 400 plus degree Fahrenheit range, with up to 85 degrees. Normally it's about 35 to 45 degrees centigrade per kilometer depth, but upwards of about 75 to 85. Based on the data that we have identified geothermal zones in these black lines. And that's as of the National Geothermal Data Systems that we helped run back in 2015. This was kind of the state for Arizona. This is where we think these areas are based on the data that we have. But that doesn't include blind areas. So these are open areas with springs. There's some sort of surface manifestation supplemented by well data, but that doesn't include areas where there's no well data and it could be blind. And so that's where we really do need to test areas that seem to indicate that there are favorable areas. We just need to find different ways of looking for that. And that could be through geophysics, magnetotellurics, other kind of resistivity tools, or actually drilling, which would be our preference to combine all of those. All right, so back to our model. EGS can easily fit into the basin model, the plateau model. At almost any depth past about 3 kilometers, there's a good likelihood that you'll have some sort of geothermal signature that could be favorable for a variety of environments, even if it's combined or not combined, or direct use or non-direct use, low, medium, high grade, all of those are favorable. Okay, with that, we've kind of summarized gas storage potential, carbon capture sequestration, ecosystems, and EGS is one example of geothermal. All of these categories of subsurface pore space management don't come without risk. So risk assessment is a huge part of that. We'd never ignore anything like that. So this diagram just shows cartoon elements of we need to protect this thing called groundwater aquifers. That's definitely the most important thing to our state and our stakeholders. We want to protect that. Any kind of subsurface management, like this, in this case, this is just pure CCS injection. You do have a plume, you have a pressure front, you have faults, you can induce seismicity, you have leakage pathways through existing wells. There's many ways things could go sideways. And so characterization is a huge part of that, and that usually takes several wells, several tens of millions of dollars to get past that stage and into the monitoring, reporting, and verification stage. DOA's got a pretty good track record with EPA on managing sites like this through monitor, reporting, and verification plans. They're extremely robust, they're very expensive to develop, and once you get them and you get the permit to inject, you have to maintain those not through the life cycle of the project, but past the life cycle after they've left, and that state is left with the liability of dealing with that. And so the risks are manageable. That's been shown, tried and true, after 50 years of doing this. At least we know that the risks are manageable. But without any kind of pore space regulation or statutes that define and clearly define the rules of how pore space is managed between the surface owners, the mineral rights owners, and the subsurface storage operators, then you're going to have problems down the road in terms of litigation. So we try and work with the Interstate Oil and Gas Compact, our Arizona Department of Environmental Quality, and the Oil and Gas Commission with Arizona to help sort of put those rules out in front using, I guess, leveraging our relationships with our state partners. New Mexico has a lot of experience with this, but they don't have, they're still working on revising their statutes for pore space infringement, liability, and ownership. So these are really important, and I think this is equally important because Arizona will have underground injection control primacy later this year for classes 1, 2, 3, 5, and 6. And that is separate and independent from pore space regulation and addressing long-term liability. So the state's aware of this, but they haven't really acted on it yet. The Oil and Gas Commission will be submitting revised statutes for rulemaking in a couple of months, and hopefully they are talking with DEQ about how that meshes with the UIC program for injection. They're looking at Texas and Wyoming and North Dakota because those 3 states have primacy. They have been dealing with these, and they have these regulations on the books. So that's all kind of going on in the background right now, which is really kind of encouraging. Even though we don't have several of these projects that operate in this space, I think our operators and stakeholders see that potential and the problems that come with it. So they're trying to get out in advance of that. Okay, the last 2 slides, or this is the third from the last slide. How are we doing on time? I lost all track of time. Okay. So the slides that Tawnya presented, putting in the model with the gas storage and CCS, CCUS, carbon dioxide removal, geothermal. If you look at them all in sort of a system setting, Arizona can accommodate several of these sites. And that's why our CO2 project in Harquahela has some attractiveness to it because it has bedded salts. You know, there's gas storage potential, there's carbon dioxide sequestration potential, there's carbon dioxide mineralization potential, geothermal potential, saltwater disposal potential. All of that within one site is really attractive. And that's one of 88 basins, or about, well, roughly 55 basins that meet these kinds of requirements. Maybe not all of them, but this is the one that we chose first. There are several other basins that look like this. So if you're a data center, or if you're an industry that's looking at waste heat and you want to meet your net negative or net neutral goals, but you need to rely on methane, you know, for 10 or 20 years, then you need options. And so some of these things can fill that gap, and that's what we've seen. We get approached almost once or twice a week from industry saying, hey, where can we put our waste? Where can we build this energy reserve? That's crazy, we can't handle that. You know, so we try and build coalitions and partnerships to help sort of work together, especially with the utilities. I'm going to give a lot of credit to the APS, TEP, and SRP, because without them, you know, they've already have these plans for 2030, 2040, and 2050, and their plans include this kind of sort of a la carte menu, at least in a dreamy sense. We just need to make it a reality. On the plateau, this is Arizona's plateau, so you can utilize some of the same features. There's bedded salts, there's pore space, there's depth, there's geothermal potential. So all of these things exist on the plateau. A little different geology, but these are the mechanisms for which there are multiple carbon-safe projects and geothermal projects, and not gas storage, but at least on those last two, Utah, Colorado, and New Mexico are operating on this model because they're part of the Colorado Plateau. And so that's how they're utilizing this in a very similar way. All right, the last slide, these are just some of the projects that we are working on. We had a really difficult time trying to put this slide together because some of it's just statewide. It's just this big blob of statewide activities. But if we go back to about 2008 to 2011, 2014, 2015, we did have several CCS-related papers that tried to address, hey, here's the biggest basin, here's what it looks like, here's the potential. And almost all of them actually were inconclusive because we didn't have enough data. I think this time around we're trying to get a little bit beyond that to not, I guess, just trying to use the data that we do have to leverage new data collection and acquisition. And we've had multiple geothermal projects over the years since the 1970s to 2016. And so that helped to kind of put together that map that we showed a few slides back. In terms of active projects, right now we have 3 statewide projects. We have the Four Corners Regional Initiative led by New Mexico Tech, where we're a part of that, and that identifies Arizona's resources in a CCUS ecosystem. That also dovetails nicely with the regional direct air capture hub that's led by ASU. And so that hub is basically designed for direct air capture businesses to identify, utilize, and sequester captured carbon from direct air capture. And that mainly focuses on the Paradox Basin, the San Juan Basin, and the St. John's CO2 dome that make up the DAC hub. And Lisa Thompson also, she leads the Ex situ mafic mineralization project. This focuses just on 3 areas: the San Geronimo volcanic field down here, Spring River volcanic field, and San Francisco volcanic field. And those are really just trying to do enough geochemical mapping of basalts for chemical reactivity and mineralization. So lots of cool projects. The CO2 HQ we're really excited about. This one is in Harquahala Basin over here. And what else? And then the red stars are areas that we've spent a little more time focusing on new projects and plays that industry is looking at, they're interested in, stakeholders are interested in those. And so we see some of them will probably drop off. Some have popped up and dropped off in the last couple of years. Maybe some of them will stick. But I feel pretty confident that given the track record, some of these are going to stick. And then the last point I want to make here is that these yellow stars are areas that DOE has funded these carbon storage, CCS project sites, geothermal sites that are ongoing at the present. And we're really excited to be a part of that group because we've been part of this Western Regional Initiative with 13 states over the last 5 years. We've formed a lot of relationships with California and our neighboring states and the northern states in the West. And that has really led to a huge learning curve for us as a group to learn what other states are doing in this environment versus that environment, and this stratigraphy and that stratigraphy. So we get a lot of hat off to DOE for funding these programs that have been really helpful and allowed all of our states, including ourselves, to grow into not just CCS, but a CCS ecosystem or geothermal ecosystem. Hopefully that'll be the next boom, like I said. So with that, thank you again, and we're happy to entertain any questions. Here we go. Oh, no.
Yes? Okay. So where's the well that has the 400 C temperature bottom?
Dang it. I knew someone was going to ask it. It'll have to be you. Yeah, all right. Here we go. So ironically, those high temperature wells are not even in these black circles. One is over, I think it's this one right here. I could be wrong, going off memory. Another one's right here, east of Phoenix. It must be the Ray Mine. Oh, that's the Ray Mine. And I think this one right here. And I'm sure there are other people in the room that know a lot more than we do, because the Clifton-Morenci area is a really big hotspot, and they've got many wells that are in the 10 to 15,000 foot range. We don't have access to a lot of that data, so I should assume those are pretty warm because they've received, I think, $80 million from DOE to advance geothermal in that area. So we knew that was a hot area.
Okay, I have another question, not related to that one, but in terms of developing this stuff, you mentioned Fervo. I think that's the company in southwestern Utah. But are there? How do you see that working with the kind of data, the basic data that you're developing versus potential for commercial development of geothermal resources? Is what I'm talking about.
So the question is, how do you see us advancing to a site that's like Fervo in the site in southwestern Utah, in Arizona?
Yeah.
Okay. Well, I think, if it's a blind system, we have these data sets that we can kind of operate off of. We have this model we work off of, and then the gradients and the flux. So I think that's one of the places we would start. There's a ton of magnetotellurics out there that we don't have access to, and that would be another data set that we could look for. But before any of that were to actually happen, I think a demonstration with a partnership in mind would be one of the better places to start, because there are several that want to advance and see some kind of area be explored a little bit further. But in terms of like how to go about that, like how would that be funded? Would it be through DOE or would it be through private capital? We don't really know yet. We do see the geotechnical office is planning, and they've been saying for months now that they plan to drop the notice of funding opportunities January, February, March of this year. So we've been kind of keeping an eye out for that. I'm not sure what the volume of the funding would be, but it's supposed to come out of the Inflation Reduction Act. And the language in there is, we just have no clue. So even with those partners that have already stepped in line and said, we want to do a geothermal project. We've asked that question as well, like, oh, how do you plan to do that? What do you envision doing that? Because we don't really have I think our approach might be a little different than sort of a demonstration, to submit for financial assistance from DOE. Sorry, that's not a really direct answer. But until that NOFO drops, we're just really not spending a lot of energy on it.
There are a number of people.
Question there.
Oh, there's a question. Go ahead.
Can you hear me? Yeah. Great presentation, thank you. I was wondering, what would be the CO2 source for that carbon safe 2 project? Are there any nearby emitters or pipeline or something or is it direct air capture? What were you thinking about it?
This is for the CO2 HQ project in Harquahela.
Yes.
We have commitment from the 3 utilities that operate, well, actually 4. We've got one of the other operators of the natural gas-fired power plant as part of the partnership team. So those total about 5 natural gas-powered plants, totaling about around 11 million tons per year in that vicinity. And that's separate from the nuclear power facility. Obviously, they don't have emissions. So those 5 sources are more than enough. It's actually probably too much. I don't think we can fit 11 million tons down that hole a year. So direct air capture companies are also part of the partnership team. So there's some legacy CO2 that helps those utilities make up for the gap, that they can't inject all of it. So they'll just pay for credits to offset the rest. But that's the rough makeup of the CO2 sources. Yep.
There are some people that are following this remotely. They're streaming this. If they have any questions, this would be a good time for them to unmute themselves and chat.
Great.
Somebody's raising their hand.
Okay.
Ruben's.
Can you go ahead? Oh, is he speaking though? Yeah. We do have somebody who's trying to ask a question, but muting is an issue now.
Well, chat, maybe, yeah.
What is his name? Drew? Gru. Hey, Gru, you'll have to unmute yourself to be able to ask your question. Otherwise, you'd have to put it into the chat.
He has his microphone sources switched, that's why. He's unmuted, but he needs to change his mic on his end.
How do we tell it?
That's what's going on. All right, he typed, what is the deepest well drilled in the Mohawk Valley?
What is the deepest well drilled in the Mohawk Valley in southwestern Arizona?
I think 2,000 feet.
Okay.
Yeah, maybe, probably 2,000 feet. Yep. I know Mohawk is one of those basins that looks really promising. A question up here? Oh, yeah.
Thank you.
All right, are we on? Yeah, okay. I'm curious about the Utah side. I'm from Utah, and that Milford side has been going for a very long time. And how did it get selected for the enhanced geothermal?
Oh, I don't know.
It's been going for ages.
Yeah, I think, actually, you know what? Yeah, we don't know. We're not as familiar with that site. We would love to be invited to a field trip to go see. We have been in communications with one of the state geologists. No, we haven't. No, we're thinking about it. Yeah.
The Utah site was there was I don't remember because you weren't involved, but there was like 10 years ago or something. DOE put out sort of a challenge grant to do some kind of research facility to test geothermal. I think enhanced geothermal at that point, but the technology had been evolving so much during the process. But I think Utah and Nevada were the final final, it came down between Utah and Nevada, and Utah won out. But I think it basically was just to characterize the deep subsurface and the potential for geothermal energy production. But you know, the site, I think they started working on it probably 6, 7, 8 years ago, and since that time, the technologies, the drilling technologies have changed. Using oil industry drilling technologies in this context is something that's just been done in the past 5 years since the Forge project was started. So it's really evolving all the time. But I don't think in terms of
I can take a stab at that. I've been to the Milford site that was developed by Phillips Petroleum, late 80s, and still operating. This site is down in Fillmore, down the road, down in the valley, and it's a new blind site where they've done a lot of the drilling and testing and R&D. So separate from the Milford site that's been operating for at least 20 years.
Yeah, and I believe it started out in 2020 with about maybe, no, I'm stuck on the number 20, with about $20 million startup. But now, since then, it's grown to over 200 million. So there's a reason why they've done that, and I think DOE provided an additional influx of cash and a no-cost extension. Well, that would be a cost extension, but they've got an extension to help that project keep going. So there's a lot of incentives behind it. But as regarding the geology and sort of the progress, I don't know much about it. I should, because all of it, one of the things that they're touting is the transparency of it. So as soon as the data comes in, they release it right away. There's no hold on the data, which is unusual for a DOE project. They usually have a hold for 3 or 5 years. Thank you. That was great. Yeah, Mike.
All right, thank you for the talk. That was wonderful, good information. Yes. Oh, I'm sorry. Did I? Okay. Now I know the classification of basins in the Colorado River corridor get a little messy because of like inherited structures and past history, but is there a certain advantage of targeting these half-style or these basin and range style half-graben basins over, say, the pull-apart basins along the corridor?
Along the Colorado River corridor?
Yeah.
The lower Colorado River? Yeah, right west of Grand Wash. Well, you know, I think that the concepts come up once in a while, like, okay, why not here? Because some of the basins are amazingly deep. You know, certainly past any kind of supercritical CO2 threshold. If it's CCS, is that what that particular type of pore space, was it for CCS?
Yes, for, well, either storage or sequestration, yes.
Okay. Yeah, for CCS, the depth is certainly there. I think we haven't really looked into that, probably because California hasn't done anything either. And then you have to wrestle with the idea of that space, you know, in terms of it's complex. It's a similar reason why we've kind of shied away from Luke Basin in Phoenix. You know, it's really attractive for so many reasons, but it's covered by a huge metropolis. And we know that's typically a problem when it comes to permitting. And so a lot of effort has kind of been directed towards other areas that might be more rural or unexplored, that have, I guess, the least amount of permitting friction that comes along with it. Those are just general concepts that I think we kind of internally talked through as a group, but that's certainly shared with the industry that comes in.
Kind of unrelated to the talk, but Tawnya mentioned that there's now a core repository open, or a core warehouse.
Oh yeah, core repository.
With the U of A or the survey. Can we know a little bit more about that? Is that like a library type of setup that's open to the public or to companies? Can companies donate core to that repository?
Well, you can hand that microphone to that person right there.
On my to-do list is to release the OFR that documents the updated version of the AZGS core repository. We do have a curated collection of donated drill core, largely donated between the 1980s and mid-2000s, that we've taken back out of storage and made available again. We have it all photographed. Our view is to get it onto a web map so that you can first see all of our, the photographs, any logs, and hopefully be able to digitally look at it. We're in a very small building, and we don't have a warehouse, so it's just, I took a room over and I shoved it all in there. So we need a bit of a heads up, but I'm trying to, in the next 2 months probably, have an official announcement that this is available, and we're happy to share it. I would love to accept more core, but we're pretty at capacity already. Yeah, when the university recovers from its financial crisis, prior to that, we were exploring building a facility to actually store core for the next few decades. That's probably what we have to do, yeah. But yeah.
We do have a question in the chat.
Oh, great. Mike? Yeah.
From Jeffrey Evans, or is it from Justin?
Justin.
Justin. Okay. Justin says, I can see proximity to metropolitan area being a double-edged sword. Point source emissions benefit from a nearby storage site, but those sites might embitter locals in the area. What steps is AZGS taking to inform the average Arizonan on this and CUS/EGS generally?
Okay, I'll try and answer that. So what would be help me out, Mike,
I think he's asking, this individual's asking, what sort of steps are AZGS taking to inform people about the potential for doing this in the state of Arizona, the risks, the hazards, and the benefits?
That's a great question. We've been sort of more locally site-oriented when it comes to community engagement. And on a statewide level, we've been more focused on engagement with the stakeholders, the utilities, the governor's office. We've presented to them several times, like, hey, here are the issues that are statewide oriented that we feel are important, that where education and outreach need to come in hand or in advance of or at the same time. So those are more of the statewide efforts. The local sites like the CO2 in Harquahala Valley, we built a story map that was dedicated to that basin that addressed what CCS is, what are the risks, who are the stakeholders, how does it work, just to put all of that out there. And we've used that tool to to provide that to the statewide community as well. So we'd like to do more of that because the story map works really well in terms of an online sort of presence. So we recommend that. I think that link it is in the presentation, in the PowerPoint that will be released, so that link is there for the story map, and that's kind of the direction that I think we'd like to continue to grow in, because without outreach and education, there's no way any of these projects can move forward. I mean, that's pretty clear, and that's also the perspective from the tribes, especially the Navajo Nation, where they have a separate primacy that they're seeking through EPA. But they're also in this space, so there's a lot of cross-communication that comes, and that's the number one concern is education on the topic and engagement, identity, and ownership. And that's what I think the communities will want on every level, whether it's site-based or regionally based. That's a good question.
Thanks, Tanya and Brian. I think it was a great talk. I want to give them another round of applause. Come on up, come on up. So Eric Seedorf has pretty much demanded that we start to, we had a long tradition in the Arizona Geological Society of giving, when speakers are kind enough to address us with a presentation, we had some nice hand specimens that are mounted on a little, I don't know what those little footers, whatever this is. So anyway, it turns out I have a little store at my office because of past AZGS people who've given talks, so I can get this started. I think going forward, we'll have to get more, for those of you who have nice hands, I'm looking at, have hand samples that would look nice on these kind of things. We need to get some more, nice rocks to put on these things, and then we'll go forward. We'll work with Tucson Trophy Company or something like that to get them mounted up. So we've got enough to probably handle this spring, but after that we're going to need, if anyone feels like, if you donate your hand samples that are cool, we will acknowledge you immediately. You'll feel very good about yourself. So, all right. So anyway, for these two folks who I didn't coerce them to do this, but I strongly suggested, since they work for us anyway. Thank you very much for giving a wonderful presentation. I hope you all are half as excited as I am about the prospects for these subsurface resources and geothermal